Hi everyone, my name is Daria Gangardt. I'm a second-year PhD student at the University of Birmingham, and today I'll be talking to you about some of the work I've done on spin precession. So, to get started, as most of you probably already know, black holes have two key properties, a mass and a spin. And because of general relativistic effects, the spins will be able to interact with one another when the two black holes are in the binary, merging and emitting gravitational waves. This interaction leads to also a tilt of the orbital plane, or the orbital angular momentum, which causes a modulation in the gravitational waveform. So here you can see two simplistic gravitational waves, one which is non-spinning, and you can see that both the frequency and the amplitude are increasing linearly, while below you can see some of the effects of spin precession on the waveform, and you can see that both the amplitude and the frequencies are increasing and decreasing before merger, which happens on the rightmost of the screen. So this effect is known as spin precession, and typically, ideally, we would love to be able to describe spin precession in terms of just all of the spin parameters, so both the magnitudes of the spins of the black holes, as well as their tilts respective to some frame of reference. Unfortunately, we don't constrain each of these spins equally, and therefore, typically in analysis, we use effective spin parameters such as chi-effective and chi-p. Now, chi-effective and chi-p are pretty good parameters for describing spin precession. However, they're both linear combinations of the individual spin parameters, and they can be a bit obscure when you're trying to describe what the actual system may look like at a given point in time. i.e., a chi-effective of 0.3 could mean many things, not just one spin configuration. So instead, some of my previous work looked at trying to take a different approach to the spinning of these two black holes, looking at the geometry of the system and the spin dynamics, and seeing if we can describe it in terms of what the system may look like without having to use all of the spin parameters. So before I tell you about that, a small brief introduction. So for two black holes going around one another, there are three key timescales. The orbital timescale, which describes how fast the two black holes are going around one another, and then taking the simplistic gravitational waveform, you can see this as the sinusoidal pattern. There's the precessional timescale, which is the timescale in which the orbital plane is tilting. Here you can think of it as, for example, how these envelopes in the amplitude in the waveform. And then there's also the spiraling timescale, the timescale in which the orbit is losing energy due to gravitational waves. In my previous work, we looked at defining parameters at large separations, i.e. when the gravitational field is weak. And in this case, something that's very handy is that the three timescales are very different from one another. And that means that you can not only prescribe analytical expressions that are valid as long as the two black holes are not too close to one another, but it also means that we can average over spin precession timescales, meaning that we can look at parameters that should vary on the precession timescale, but look at their evolution from large separations down to smaller ones. So going back to my previous work, as I said before, we tried to take a geometric approach to our binary. The way we did so is by, instead of looking at the individual two black holes, we looked at the motion of the orbital angular momentum, as this is the direction in which most of the gravitational wave power is emitted. For generic binary black hole binaries, the direction of the total angular momentum J will remain constant. This means that we can set up a coordinate frame and then instead see how we can describe the orbital angular momentum as it goes around J. We split the motion of L in our previous work into a polar motion and an azimuthal motion, where the azimuthal motion is our precession and the polar motion is now something that we call nutation. If there is no polar motion, i.e. no nutations, L will go around J in a cone with a fixed angle theta L. So the precession average value of theta L is our precession amplitude, and the frequency with which L moves around J is our precession frequency. Nutations introduce a raising and lowering of the orbital angular momentum. And so this induces a change in the theta L that we call the nutational amplitude, but also the frequency with which it's raising and lowering is the nutation frequency. As well as this, nutation will also mean that our azimuthal frequency, omega L, will also vary. So to complete the picture, we also included a precession frequency variation, delta omega L. So one of the key results from our previous paper is that we were able to look at how different binary properties will affect our precessional and nutational parameters. If we are interested in trying to see if trying to describe a binary as mutating or precessing using our 5 parameters, it's perhaps most interesting to look at the amplitudes of the motion, because if we can constrain an amplitude to be away from 0, we can say that we have detected mutation and precession in our binary. So here we look at 3 populations of isotropically misaligned black holes, and you can see that both of the amplitudes are maximized for highly spinning binaries, which is represented by the green curve. However, the precessional amplitude is maximized for smaller q, i.e. smaller mass ratios, while the nutational amplitude actually prefers moderate q. For both of these, events with a q that is away from the equal mass limit is favorable in order to be able to constrain a binary as precessing or mutating. Now, moving on to the actual work I would like to present here. Having taken our 5 parameters that describe spin precession, we were then interested to see if we can constrain mutation and precession in the current gravitational wave events that we have detected thus far. What does it mean to constrain a parameter? Well, typically in the field, that means that you have an uniform, uninformative prior, and then your posterior is very different from your prior. However, you wish to define very different. Additionally, one thing that one can do is to also condition your priors on the fact that you have measured certain binary properties very well, i.e. condition them on the posterior values of like the masses or chi effective, as has been done here. So here they have posteriors and priors of the effective precession spin parameter chi p. However, the priors have been conditioned on chi effective. This lets you see if you have measured any additional information on top of measuring chi effective in this case. So we construct these conditioned priors and then reformulate all of the distributions of like the prior and posterior values of the spins that LIGO releases in the parameter estimation files. And we do this for all of the events. Here, I'm showing you the results for the event GW190412. Now, the reason why I've chosen this event is because some of you may already know this. It has a very extreme mass ratio that is away from 1.
That's your 2-minute warning, Daria.
Thank you. Yep. And so ideally, this means that we'll be able to constrain precession and mutation in this event. It also has a high network SNR, which is very useful. And you can see in our results that, unfortunately, for delta theta L, the nutational amplitude, the posterior looks very similar to the priors, meaning that we're not able to constrain mutation for this event, something that we see across the population. However, the precessional amplitude, bracket theta L, the posterior is very different from the priors, meaning that we can say that this event is precessing, especially because our posterior is constrained away from a value of 0, which is nice. As I said, I repeat this analysis for all of the events across the gravitational wave catalogs. And then here, to summarize the results, we use the Hellinger distance as a number to quantify how different a prior is from its posterior, where a value of 1 means that they're very different and a value of 0 means that they're not. Across the population, we find that we cannot constrain mutation very well at all. Our Hellinger distances go between 0 and 0.2, and even for like the highlighted events here, it's still not very high. However, we are able to constrain precession for some of the events across the catalog. As you can see that the precessional amplitude goes between 0 and 1 in the scale on the y-axis, and there are some events that have some very high Hellinger distance values. To conclude, we're not able to constrain mutation in the catalog. However, we were able to synthesize an injection that would have a high mutational amplitude. And you can see here that for this synthetic injection, the posterior is constrained away from the priors. This means that we may be able to detect mutation in the upcoming LIGO runs. Thank you very much. And are there any questions?
Thank you very much, Sarah. That's really good. So we just wait for some questions to come in. I guess I can ask you, do you have like an idea if there's like a threshold in SNR you'd need to detect this? Or...
So the event that you see here, which is, I think, one of the, which is the only case where I would confidently say that we detected constrained mutation specifically, the SNR is quite high. However, this is, I think, just we place it fairly reasonably away from Earth, and I think that so here I think the network SNR was about 30 or 40. I can't quite remember, but those are still roughly in a single detector. It was something like SNR 20. So let's hope.
Okay, great. No, thank you very much. I can't see any other questions coming in. So thank you very much, Sarah.